The interactions of subatomic particles can be complex and difficult to understand. The talented physicist and communicator Richard Feynman introduced a method of drawing diagrams to help our comprehension. At first glance, these diagrams look like graphs or like vector diagrams, but they are neither. They are schematic pictures with rules for their interpretation. In the diagrams, time is represented as going upwards, and space, in general terms, goes horizontally. Unfortunately, this is not an international convention, and in some diagrams, time is the quantity moving horizontally. Fermions involved in an interaction are shown as solid lines. In this example, the interaction between the two electrons is conveyed by a photon, a virtual photon, and that is the wavy line in the diagram. The side-to-side displacement in this diagram has no meaning other than to show that the particles suffer a change in momentum due to the interaction between them. There is some commonality in the use of the symbols, but no complete agreement. Those shown here are used by the Institute of Physics. A solid line indicates a fermion. The wavy line is a photon, the exchange particle associated with electromagnetic interactions. The looped line is a gluon, associated with strong interactions. And finally, the dashed line is a boson, for example either W or Z, associated with the weak interactions between quarks and leptons. One final rule is that antiparticles are shown by arrows pointing downwards, as in this example of the interaction between two positrons. Let's draw a first example diagram of beta emission from the nucleus of an atom. Remember that in these diagrams the progression of time is shown upwards and space is horizontally. Beta particles, which are fast electrons, are emitted from the nucleus from a neutron. This forms a proton emitting a W- boson. This boson has a brief or virtual existence before it splits into two further particles. That is a fast-moving electron, which is the beta radiation, and a neutrino. To preserve the overall lepton number in this process, the neutrino is an antineutrino. The arrow therefore points downwards. Notes on the rules for baryon number conservation, lepton number conservation and strangeness can be found on the website. This diagram can be extended further to show the change in the quark nature within the neutron and proton. The neutron consists of 3 quarks, as does the proton. In this process, one of the 2 down quarks in the neutron becomes an up quark in the proton. My next example is of a positron emitted from a proton to form a neutron. Since a neutron is fundamentally less stable than a proton, energy is required to make this reaction happen. This energy comes from the binding energy of the remainder of the nucleons in the nucleus. The transformation of proton to neutron is accompanied by the emission of a W+ boson. This in turn produces 2 particles, the positron and a neutrino. Because the positron is the antiparticle of an electron, the arrow on the diagram is shown downwards. As before, we can add to the diagram to show the change in nature of the quarks. One of the 2 up quarks in the proton changes into a down quark, so producing the 2 down quarks and 1 up quark of the neutron. The video Beta Decay Transitions in this series explains this whole process in rather more detail. The next example is the capture of an electron by a proton. Both fermions are drawn with solid lines, both with arrows pointing upwards. The exchange particle must carry the negative charge to neutralize the proton, and therefore must be a W- boson. The result of this is that a neutron is formed. That is, together with a neutrino. That preserves both the lepton number and the boson number during the interaction. Neutrinos rarely interact with other matter. However, it does occasionally happen, and in this occasion both of the particles are shown with solid lines, arrows upwards. The exchange particle between them is a boson, a Z boson, with 0 superscript, since there is no exchange of charge. The interaction will not change the nature of these two particles, but it will change the momentum. Notes to support this video may be downloaded from the website.